Hello. Imagine you are standing in front of a massive library. The shelves extend endlessly, and any book you need seems instantly accessible. Now imagine someone whispers into your ear. Actually, only one small cupboard behind you is real. The rest of the library is an illusion that rearranges itself every time you reach for a book. And that exactly is what virtual memory does. Now one can see this particular picture in front of you. This picture shows the concept very beautifully. Virtual address space swirling in like a galaxy, funneled through page tables and the memory management unit, and finally reaching RAM and the secondary storage. Virtual memory creates the illusion of vast, infinite memory, even though your system might physically have only 4, 8, or 16 GB. It achieves this illusion by mixing hardware, like for example, memory management unit, and software techniques like paging and swapping so smoothly that programs never realize this truth. Now, how many apps do you keep open at once when you start your device? It could be laptop, mobile, desktop. 5, 10, 30. Modern systems have 4 till 32 GB RAM, but applications today are memory hungry. Google Chrome alone can take multiple gigabytes. Imagine if every running program needed to fit entirely inside the RAM. The moment you open two large applications, a Photoshop and a heavy game, you would see a message like, please close other applications, or probably not enough memory available. And this is when, without virtual memory, apps would be crashing often, multitasking would be impossible, users would constantly close applications just to continue working. Think of physical RAM as a small hotel with limited rooms. Virtual memory transforms that hotel into a giant city with infinite hotels. Most rooms exist only on paper until someone actually needs them. And this solves the biggest limitation of physical memory. So let us try to understand what is virtual memory. Virtual memory behaves like a magician who says, no matter how many boxes you need, I will give you more. Programs see a large continuous block of memory, maybe 4 TB for a while, even though the machine might have only 8 GB. For example, a video editor may load a project that appears to require 30 GB. In reality, only the parts currently being edited needed to be in the RAM. The rest slips quietly on the disk. Each program thinks this memory region is mine. No one else exists. If two of you write on two whiteboards with the same marker numbers, marker 1, marker 2, it doesn't conflict because each whiteboard is separate. Similarly, every program gets its own address space. That is called as address space separation. And lastly, programs don't worry about RAM availability. They just ask for memory. The operating system silently provides it, even if the real RAM is full. And the program never knows where exactly its data is, whether it is on RAM, disk, or swapped out, or even it is in cache. Everything just works automatically, and that's what is transparent operation. The CPU generates virtual address space while running instructions, like writing letters addressed to imaginary streets. The memory management unit is like a postman. It instantly maps those imaginary addresses to real locations in RAM. If the required data is not in the RAM, the operating system quietly sends a request to fetch it from the disk. Imagine you ask for a book in a library. The library instantly knows or the librarian instantly knows whether it's on the shelf or stored in the basement. And if it is in basement, they run and bring it for you. This teamwork allows the CPU, memory management unit, and operating system to maintain smooth multitasking, continuous work, and results to no crashes even when RAM is full. And this invisible cooperation is what powers the modern computing. Paging is a technique that makes the illusion of infinite memory practical. Virtual memory is split into small pieces called pages, often in 4 KB with the operating systems. Imagine breaking a giant novel into tiny bookmark sized cards. You don't need to the whole book at once, just the cards relevant to the current scene. A physical RAM is also split into frames of the same size. Pages not required right now go to the disk, like storing extra book cards in boxes. And when program needs a page that is not in the RAM, the operating system swaps it into from the disk. And if RAM is full, another page is swapped out, and that is called as swapping. Your PC behaves like a student with a small desk that is RAM and a huge backpack that is a disk. Only a few books fit in on the desk. When one book is needed, the student takes it from the backpack and replaces another book on the desk. And the dynamic movement is what enables the multitasking. While paging divides memory into fixed size pages, segmentation divides it into some logical chunks like code segment, data segment, stack segment. Imagine you are organizing your house by function: kitchen, bedroom, study room, not fixed size tiles. Each room can grow and shrink based on the need, but the structure becomes harder to manage. Segmentation offers flexibility but introduces complexity. Variable sizes, external fragmentation, and complicated memory management would be the issues. And this is why the modern systems use paging or a combination of both, which we probably can see with excessive architecture. Now, virtual memory enables several key abilities. Runs the program larger than the RAM, editing a 4K movie on just the 8 GB RAM on a machine. Only the currently visible clips need to be in RAM, the rest stays on the disk. It allows many programs simultaneously. Each program lives in a private space, they never collide. It protects the programs from each other. If one app crashes and writes to random memory, it cannot damage others. And lastly, it simplifies programming. Developers don't need a special memory strategies. They simply assume large continuous space. And virtual memory makes computers feel far more powerful than their physical limits. Let's make a clear understanding by taking an example like paging in action. Let's take the example of web browser. First stage would be browser launch. When you open the Chrome or Firefox or Edge, only the visible tabs pages are loaded into RAM. The background tabs, that is other tabs, they may be huge, video players, large documents, etc. Their pages quietly move on to the disk to save the RAM. And when you click a different tab, that is tab switching, the operating system quickly swaps the pages belonging to that tab. And this is seamless experience. Even though massive page movements happen underneath, you see instant tab switching, and this illusion of smoothness is one of the greatest achievement of virtual memory. Think of it like a restaurant kitchen. Only the dishes requested by customers stay on the counter. The rest stay refrigerated. When someone orders a new dish, it comes from the backroom storage instantly. And that's what the paging actually is. Virtual memory is powerful, but definitely not free. Heavy use can introduce several issues. Memory pressures. Too many active applications may fill up the RAM. Fetching a page from the disk is thousands of times slower than from the RAM, and that causes fetch fault. Reading from your disk, that is RAM, takes 1 second, but running to a distant storeroom, that is disk, takes 2 minutes. Then it introduces thrashing. The system spends more time swapping pages than doing the real work. Like a student constantly switching books every 5 seconds, but never actually is reading, which introduces the disk overload. This becomes slower than RAM because of the continuous swapping, and it slows the entire system. It results to switching overhead too. Jumping between applications can cause frequent page loads or unloads. Also results to energy consumption. Storage devices, the CPU, work harder due to heavy paging activity, and user gets impacted. Short freezes, app delays, slow switching, all caused by excessive paging. So virtual memory is one of the most important inventions in computing. It creates an illusion of infinite memory, allowing modern systems to multitask efficiently, run large applications, and stay stable even under heavy workloads. And this success comes from a partnership between hardware, that is a memory management unit, cache, page tables, and OS software, paging algorithms, swapping strategies, protection mechanisms. So when you understand virtual memory, you understand how computers manage to juggle dozens of tasks so gracefully. How laptops with limited RAM can still run giant applications. How phones handle the multiple applications instantly. And how the servers manage thousands of processes without breaking. Virtual memory is the quiet hero that makes modern computing smooth. Thank you.